speaker, Yongxiang Hu from NASA Langley Research Center. As you can see, we're trying to get more scientists from other centers as well. And Yong has been with NASA Langley since 1999 and has been supporting the very famous mission known as CALIPSO, lidar, and infrared pathfinder satellite observation mission, or simply known as CALIPSO, and participated extensively in algorithm developments. He was also a science team member on the lidar, remote sensing, and his PhD actually is from University of Alaska, Fairbanks, way back in 1994. And originated from China, obtained his Bachelor of Science in 1985 from Peking University. And he has done outstanding work, been recognized professionally in many places. And here at NASA, he has won NASA Exceptional Achievement Award way back in 2008. And Yongxiang also has authored, listen this, he has authored more than 200 peer-reviewed journal articles. And he also has a book on remote sensing and a few patents, right? So just figure that out, right? That's outstanding. So a good thing. So today, he's here going to talk about a very interesting topic on some of the work that he has done with CALIPSO, and now he wants to apply it to snow and ice. Personally, because I've been involved with the snow community, I'm very familiar with the work he's trying to do on snow and ice. And I don't want to preempt all the details of what he's going to talk about. With that short introduction, I want to welcome our speaker today, Yong. The floor is yours.
Yeah, thank you, Charles. Yeah, the topic of my talk today is about a potential positive feedback mechanism in the Arctic. So the basic concept is when the Arctic starts to warm up, the snow is going to become a little bit kind of thinner, which will make the ice algae more productive because there's a little bit more sunlight coming in earlier during the spring. And there, as a result, this ice algae will release some of the cloud forming aerosols, mainly the iodic acid. And then as a result, that will the clouds will be a very good greenhouse that will warm up the snow and ice below the clouds in the spring. So it opens up the needs faster every year, and then that will allow more sunlight to go into the ocean, and then it will increase the melting in the fall. So that's the kind of process that I'm trying to look at, and I'll introduce what I've done so far and what I'm doing right now, and hopefully for time we'll probably discuss what we may do next. So here is the the summary, the brief summary of the talk. So I would first kind of introduce the cloud microphysical properties that we developed using the CALIPSO measurements, and we will talk a little bit about the findings using these cloud properties. So what we found is a very good spatial and temporal correlation between the cloud droplet number concentration and the ice algal biomass. And then I'm going to talk a little bit about snow depths, because snow depths is a key part of the hypothesis and is very important in terms of understanding the ice algal biomass. So as I'm going to talk about a new concept of using ISAT2's multiple scattering signal to derive the snow depth. So there has been a lot of interest in the connection between the biosphere and the cryosphere and the hemisphere. So and there has been this studies in the past talking about how the phytoplanktons absorb some of the sunlight, especially the blue light, and as a result, reduce the reflection of the blue light by the molecules in the water. So as a result, it will make it warmer, and it will amplify the warming. For about a couple of watts per square meter, it will double the biomass of phytoplankton in Arctic. So, and this is not what I'm going to talk about. I'm going to talk about mostly about the feedback mechanism. Yeah. Basically the clouds, especially the springtime clouds. So the idea was started when I was reading Salzman's paper in 2006. That's on the right-hand side. So in this paper, he was looking at the ice core, and he found that there's some good correlation between the MSA, which is methane sulfur kind of acid, MSA, and the temperature. So O18 is the proxy of the temperature in ice core. So they found some good correlation. And kind of suggesting, for some reason, whenever the Arctic or Antarctic, this time is Antarctic for this case, when the polar region warms up, we see more kind of evidence of this kind of the aerosols, which are associated with life, mostly, I mean, Arctic, whatever the primary productivity there. So that's a kind of indication there. And then on the left-hand side, people have been looking at the ensembled kind of models. Basically, they look at the model prediction of the September sea ice retreat, and they find very good correlation between the sea ice retreat in the fall and the springtime cloud amount, especially the low-level clouds. So the idea in there is the low-level clouds in the spring, they don't do much about sunlight because the snow and the ice are the snow is very bright already in the spring. So adding clouds doesn't really add too much of, I mean, kind of change too much about the sunlight. But what it really does is it sends down a lot of infrared radiation and downward to the snow surface and melt the snow in the spring. So make it melting much faster, and then that will increase the amount of energy goes into the ocean, and that causes the increase of the sea ice retreat in the fall. And then there's another community which mostly are the Arctic in situ measurement folks in Europe. They think there is a big problem of algae acid in terms of amplifying the Arctic warming. So there's a lot of publication in that community. So they basically consider that there's a big part of the process that is causing Arctic to melt faster was not really well understood and well represented in the current models. So basically, what their kind of studies are showing is during the spring there's quite a bit of snow and ice algal blooms, and they are going to release the iodic acid, which is much more efficient comparing with sulfuric acid in terms of nucleation process and the particle growth process. So they're basically a lot faster. So it's more efficient. I mean, more than 100 years ago, people already knew that. I mean, for the new particle formation, the most efficient ones are things like iodine and the bromine. Bromine is probably the most efficient. And then there's relatively less efficient comparing with that is the sulfate. The sulfate has been very important. We know that the DMS and the MSA, which are the sulfate-related kind of process, that are very important cloud nuclei for seeding the clouds. But in Arctic, people found out that the iodic acid is the primary cause of the cloud seeding, not necessarily the sulfuric-related process. So what I'm going to do is going to introduce some of my studies using CALIPSO data to show that there is good kind of correlation among ice algal biomass and the no level cloud number density and the cloud fraction. I'll first talk about the result. So left-hand side is the model kind of the results of the April the ice algal biomass. So this is in the logarithmic kind of term. The unit is mg per cubic meter. So the right-hand side is the CALIPSO derived number concentration in the springtime earth clouds, and you can almost see very good correlation. The red part, which are more than 200 per cc of particles in the water cloud. They are almost basically really correlate well, especially with where the high ice algal biomass is. Also, if we look at the temporal side, so the x-axis is the number of days since January 1st, inside is quite a few years of averaging. And then the blue line is the ice algal biomass of the Arctic. So I integrate everything in Arctic, and then I look at how they change with the time of the year. So basically, you can see they peak up almost at the same time. The red one is the droplet number concentration of the clouds. So they pick up almost exactly the same time, and then the clouds are the high number concentration are still there for a while, because once the ice algal kind of ice algae send some of the particles in the air, it took a little bit while to for the clouds to clean them up. And this is the low-level cloud kind of the red one is the cloud amount, the cloud fraction, yeah. And then the blue is the ice algal biomass. You can see there are, kind of correlation. There's a little bit delay from year to year, and there's always a little bit delay in the peak of cloud fraction. So we don't know whether it's completely. What fraction of the of this coronation is due to ice algae's cloud seeding, and what fractions due to the water vapor from the needs, right? So when the ice starts to crack, and you got a lot of water vapor coming up, so that could also be the primary reason. But we do see some correlation there. So I'll talk a little bit about the simple physics behind the derivation of microphysics from lidar. So normally, when people talk about lidar, normally they consider it's mainly for aerosols, but lidar actually, the multiple scattering signal of lidar has a lot of microphysics of clouds there. Actually, it could tell almost everything about clouds. So in this paper I published last year, we just took a very small fraction of what we can do about clouds with lidar signal. So basically, we can derive size. So the size is we could derive the so-called lidar ratio, which is a function of size. And also the corner ratio plus the lidar ratio can give us basically both the size and the width of a distribution. And then we can use the several methods to derive extinction coefficient. So we could use the peak return, we could use the decay rate, and also we could use the multiple scattering, like the so-called Poisson distribution, the details, the second movement divided by the first movement. We can also derive the extinction coefficient. So there are several ways to derive that, and that is one that can never be done with passive sensors, because passive sensor can give you the column optical depths, but cannot tell within 1 cubic meter what's the extinction coefficient. So that property could be derived accurately from lidar. So once we have the extinction coefficient and the size, then we can derive both liquid water content and the number concentration. And we compared with in situ measurements, so we have lots of aircraft flights underneath the CALIPSO track, and we collected some effect radius and extinction coefficient, and they agree pretty well. So this is showing the data product I generated with CALIPSO. The upper part is the daytime, the lower part is nighttime. The left-hand side is the particle size, the right-hand side extinction coefficient. So the size change at nighttime increased tiny bit, but the extinction coefficients in some of the boundary clouds increase quite a bit at night. And we can here the left-hand side is the liquid content, and the right-hand side is number concentration. So the number density. Again, the upper part is the daytime, and the lower part is the nighttime. So you can see the number concentration between day and night. If you look at the right-hand side, or doesn't change a lot, but there are some changes in the. So the key finding from the data is during late spring, like April and May, and early June, the number concentration, the number density is very high. It's actually twice as much as in the other season. So normally in the Arctic, the number concentration for the cloud droplet in the level clouds are less than 100 per cc. But in the late spring, the springtime Arctic clouds, they are.
Young, let me interrupt.
Yeah, go ahead.
Do you want to answer questions as they come, or you want to wait until the end?
Oh, I cannot see the question. So yeah, anytime if anyone wants to ask any question, please go ahead. I will be very happy to answer during the process. Yeah.
Okay, there's a question here which from Ian. He says, "Do we know what is driving the second peak?" I don't know. Ian, were you referring to the previous chart?
Yeah, it was a previous chart. It's all right, Kateva. We can keep going. I can ask that one at the end. It was kind of idle curiosity.
Oh, which one? You mean here?
No, if you drop back, it was where you had the ice algae bloom and the
yeah,
that one right there.
Yeah. Oh, yeah, okay.
One more actually.
Okay.
One more slide to the right when you have the time series.
Oh, that one?
No, sorry, it was the same red-green color scheme, but you had a time series. Yeah.
That this one?
Yeah.
Oh.
Yeah, we're up sequence.
The part size. Oh, okay.
Yeah, so I mean, if you look through the years, right, one of the things that just stuck out to me very quickly is there's a second peak in aerosol particles in those clouds, and there's also seems to be a trend through time. That peak is not present in the early years and then increasingly prominent in the out years. And I was really just curious if you knew what was driving that second peak and also the sort of apparent change in it.
Oh, and this are we looking at the same? This is the particle size versus the lidar ratio stuff.
I think it's two slides
right.
back. 2 slides back.
2 slides back.
Thanks,
okay. This one. Oh,
that one. Yeah.
Yeah. Oh, yeah. Yeah. Good point. Yeah. So in the summer there is another peak. I think it's due to the summer with the fall, right? So and that's most likely associated with it's possible possibly due to the DMS related stuff. So I don't know.
Okay.
It's a good question. Yeah, because in the summer, once we're in the full summer and early fall, there was the time that we have a lot of DMS because the Arctic. I mean, that's in the water. So it's not the ice algae. It's most likely. Yeah, really good question. Yes. Yeah,
Thanks.
but I don't know. But that's what the data shows. So I don't know what's causing it. Good question. Yeah. Good.
Thanks.
Yeah, good point. Yeah, good catch. Yeah. So so basically, I mean, we can see. Yeah. So I'm sorry I cannot see the questions. So if you have questions, just interrupt me. Okay. I'll be very happy to answer questions. That just ask me to wait a minute and then you raise your question. I will answer. So mainly, I mean, in the springtime, that's the real high number concentration is. So the rest of the year, you can see that they are all under 100, but just the springtime, very, very high. Similarly, in the southern hemisphere, similar situation. So this is so I'm only going to talk about Arctic today. So this is the modeling from the biomass from the models. So the models can produce I mean, basically, if you put in nutrition and you put in sunlight, the photosynthesis stuff, then you can produce some of the distribution, and this is what it is. Yeah, again, this is I mean, the regional kind of correlation. So we know that it's almost this high number concentration are almost always above the places where the ice algal biomass is very high. And then this is another kind of a spatial correlation. This is just point by point, just from any time of the year. You can see that the location where we have high biomass. The x-axis is the logarithmic of the biomass. The y-axis is the number density. So it's you can see that it goes pretty high when the biomass goes to more than 10. Yeah, again, this is the temporal correlation here. So the also we look at the altitude dependence of the springtime cloud droplet number density, and you can see that the lower this is the cloud top, so we can only measure the cloud top. So the lower the cloud top is, the higher the number concentration, the number density of the clouds, which is very, very difficult to explain if we just use the CCN, the CN, I mean, kind of results that we derived from transport model. Use the pollution. So because normally the transport process, you have more particles operating in the atmosphere than near the surface, but this is exactly the opposite. So, so this is there's not huge amount of correlation with the MSA or the sulfuric aerosol, but there is some, I mean, with a little bit kind of a delay, and but in general, the number concentration does not really kind of increase very much with the two. Again, this is this is the x-axis is the biomass, and y is the number density. So they are kind of agreeing with each other pretty well. And again, there are sometimes the number density in the summer and the fall can go up, depends on certain year. And the cloud amount is a little different. So in the summertime also has a certain peak, exactly as yeah. So the yeah. So the to study this process, we also need to understand the intervernal changes of the snow algal biomass, which is really difficult, and it requires lots of in situ measurements for sure, because those snow and ice algal process are very buried, pretty deep, and also the bromine and the iodine, they are very, very efficient in basically grabbing any water vapor in the air and then form clouds. So they become, I mean, cloud particles very quick. It's difficult to really do very good measurements from space for ice algal, but the one thing that we may help the modelers to model the ice algal process is to have a better understanding of snow depths. So we know the snow depths correlates with I mean, it has very good relation with the ice algal kind of biomass. The reason is this ice algal they grow when there's a little bit sunlight. It's like if you have snow and the ice above them, after depth about 5, that's their sweet spot. So you just need a tiny bit of light to bloom, and the after depth 5 in terms of the diffuse flux attenuation after depth 5 of snow is about 0.2 or 0.25 meter of snow. So that's where, I mean, the ice will really like, because that's the amount of light, just enough of sunlight just go in and start the bloom. So this is the kind of process. There's lots of chemical processes which really requires the photosynthesis to have the bloom and generate the iodic acid. That's important for the particle forming process. and this process, the impact of snow depths to the snow, to the photosynthesis process was done in the laboratory, and when we showed, when you apply the light, the yellow part, then you can see both the bromine and the iodine start to pick up whenever you shoot light onto the snow. So the problem for snow depths is that snow depths are not measured very well from the current kind of satellite measurements. It's very important for the photosynthesis, but the uncertainty is pretty high. So the way that, for example, for ISAT-2, the snow depths is measured by comparing lidar and the radar. So the lidar normally in the snow community, they use lidar to find out where the top of snow is, and then they use radar to find where the top of the ice below the snow is. So the difference between the two is the snow depths.
Young, there's a question here.
Yeah, go ahead. Yeah, go ahead. I'm sorry, I didn't say the question. Sorry.
It's fine. We can just leave it for the end.
Hey, go ahead. Yeah. Go ahead.
Go ahead and
No, it was, I just was putting a comment about the summertime peak, but we can save it till the end. It's not important.
Okay. And the problem for the current method, like ISAT versus cryosat, is the radar has much bigger footprint. So the footprint match is it's an issue because we have a tiny amount of snow above. So any errors in the mismatching of the footprint can cause problem. So the lidar, the snow depth measurement lidar community normally need two trips to figure out snow depths. One trip is when there's snow, one trip is when there's no snow, and then compare the difference. But that does not really do that well for the Arctic. So the question is, can we measure snow depths directly? And the answer is yes. So develop this method based on a very simple region transfer, the random walk theory. So it's well known in the biological community that we ask on average if an ant goes into their colony, and then on average how long it has to walk inside the colony before it come out. So this is very much similar to the photon transport. In the lidar photon goes into the snow and come out. And what they found out is it's a very simple relation. It's the average path length. This is for assuming that the things goes in from every direction and every place. It's more of a statistical average of the path length. Is 4 times of the volume divided by the surface area. So this is, and then some physicists they think it may apply to light transport in a diffusive media, assuming the incident light is uniform incidence from every direction, from everywhere of any three-dimensional object. And also the higher order moments is a function of the scattering coefficient. K is the scattering coefficient. So those are the theory. So the question is whether such a theory applies to the light transport if we have not uniform incidence, but with laser pointed kind of a normal incidence to the surface, snow surface, whether the similar kind of Parsons average kind of relation with the volume versus surface area, because for the 4 times volume divided by surface area is 2 times of the snow depth. And the mean Parsons is like what we measure with lidar. So the lidar measurements is you have time and you have the amount of photon that coming back with the time difference. So it gave us the mean kind of Parsons. So whether we can derive that snow depth from this kind of average Parsons. So what I did is I did a lot of Monte Carlo simulations. So what we found out is the multiple scattering follows in the slope follows very simple gamma distribution with 2 unknowns. So one of the unknowns is the snow depth h and the alpha there. Another unknown is the scattering coefficient that we call diffuse scattering coefficient, which is 1 minus symmetry factor and times the scattering coefficient. So basically there's 2 unknowns, and we have using those 2 unknowns, we can derive the 2 parameter alpha and beta of the gamma distribution. Yeah, the reason I have been kind of trying to figure out why it is gamma instead of normal. So basically, we can consider that the reason gamma distribution is better is gamma distribution normally is a distribution of that maximize the Boltzmann entropy, which is probability times log probability, under 2 constraints. One is the mean value is a constant, and one is the logarithmic of the mean value is constant. So and for the snow process, it happens to be the mean value of the Parsons is 2 times the snow depth, and all of the higher order moments are also constants, because as a result, the logarithmic of Parsons is also constant. So that's why it's gamma. So as we can see, the snow depth, this is from model for different kind of scattering phase function. The average Parsons is always twice of the snow depth. It almost agrees very well all the time. And also, I can also derive snow depths with these higher order moments. So basically, the higher order moments, Ln, is like a higher order moments of the Parsons distribution. It's the snow depth is 2n minus 1. N is the nth moments, and the k is the scattering coefficient, the diffuse scattering coefficient. So basically, they agree pretty well if we derive the snow depths from the higher order moments for given scattering coefficient. Those are for the lidar pointing vertically, I mean, at the surface. But if there's off nadir angle, there's still a pretty good relation between the average Parsons L, which if you look at the red kind of line, and then 2 times the snow depth and the times cosine off nadir angle. So they agree very well. And also the higher order moments, you can also have the same relation that basically has you can derive it. Yeah. So we apply this to the ISET data. So we could derive the snow depths from the first 3 moments. The method 1 is the first moments, method 2 second moments, method 3 third moments of the Parsons distribution merged with set. So we just and we also derive that derive the snow depths of the snow over Arctic. Also, the 3 methods gave us almost the same.
Yeah, there are 2 questions from Ada Missy. Ada, do you want to go now?
Go ahead. Yeah.
No, I don't. I hit return before writing the questions. They're for the end.
Okay. Yeah, I'm almost at the end. So, okay. So yeah. So the summary is, we're trying to use matter measurements to study this kind of potential positive feedback processes. But we do have a long way to go, because we probably need more concentrated kind of experiments, including probably satellite and aircraft and in situ measurements to really nail down, the process, because those processes are very broad. It's not going to be done by just existing measurements. That require, many people from different community to work together to answer the question. Yeah, let's hope. Yeah, thank you for your time.